so much. Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. This is a NeEDS activity that has the support of Euro to brand the role of operations research in artificial intelligence and machine learning. So we would like to thank very much the European Union as well as Euro for giving us the opportunity to continue to run this seminar series. We are extremely pleased today to have not only the very well accomplished speaker, but also the president of Euro to open this sixth session of this online seminar series. So with this, I will give the floor to Anita Schobel, who is the president of Euro, and she will be saying a few words about the Euro Association. Thank you very much for joining today.
Thank you, Dolores. It's very nice that I'm allowed to, that I may be here to introduce some introductory words. And also from my side, a very warm welcome to all participants of this season 6 of the online seminar series on machine learning needs mathematical optimization. As Dolores said, I'm president of Euro, and what I now want to show you is what Euro is. And also you have seen on the first slide that Euro supports the online seminar series, and I want to tell you why we do so. So what is Euro? Euro is the Association of the European Operational Research Societies. Please don't confuse this with the money, because we are the association and we are even older than the money. The Euro Association has been founded in 1975. This means we are more than 25 years older than the euro currency. And when this name euro was given, we have not at all imagined that we will have also money that is called like this. So the goal of our association is certainly to promote operations research. And this is done in several ways. First of all, Euro consists of 31 operations research societies. These are all the national societies listed here. You can see the flags and you can also read out the names and have a quick check if your society belongs to our association. So as you see, most of them are in Europe, obviously. And together with these, all our members, we have different activities. So one is, which is maybe known to you, that we run 5 different publications. On the left-hand side, so you see the most prominent one, which is the European Journal of Operational Research, EJOR. Then we have 3 rather new publications and also the Euro Advanced tutorials on operational research, which can be very helpful for students to get introductory remarks for PhD topic, for example. We also run 34 working groups right now. These are listed here. I'm not reading them all out, but the newest one is quantum computing, which is on the right-hand side. And maybe the one which is closest to your seminar series is data science meets optimization. Maybe we should even add something like machine learning meets optimization. That would be maybe a future goal. Finally, Euro organizes the big conferences, which are also called Euro conferences. So there's one of these big conferences every year. In 2 years in a row, it's a Euro conference, and in the 3rd year, it's an IFOS conference for the Worldwide Association. And the next one will be next year in Copenhagen. As you see here, it's between 30th of June and 3rd of July, and you're all very welcome to join. Now, when I have introduced Euro a bit, the next question is, why does Euro support the seminar series here? And the reasons are the following. So the first reason is the seminar series is called Machine Learning Needs Mathematical Optimization. And our first reason to support this is, in fact, that we think that machine learning needs operations research. But second, we also think that operations research needs machine learning. And third, we think this should be made visible. And this is the reason why we support this series, because such an online seminar series is a great way, maybe the best way, to discuss relations between machine learning and operations research and to spread these relations to a large audience. And with this, I want to come to an end, and I wish you a successful series with a lot of talks which meet your needs, with fruitful discussions, and that you together bring our favorite disciplines forward. And I just want to say a big thank you to Dolores and Emilio and their teams for running this great series. I think we can only imagine how much work is behind the scenes. I want to thank all the speakers of this season and all of you for attending the talks. And with this, I hand over back to Dolores, who is going to introduce our first speaker today, namely Mike Baiocchi. Thank you.
Hi, folks. Should we begin our talk?
I would like to introduce you. Probably there have been some problems with the sound.
Okay.
Yes. So I would like to thank Anita Schobel, the president of Euro, and Euro for the support that has been given to this online seminar series. I would like to thank, in the name of all the organizers, Emilio, Nuria and Thomas, but also the three previous organizers, Sinia, Christina and Jasone. With this, I would like to introduce the first speaker of this season, who is Mike Baiocchi, who is an associate professor at the Department of Epidemiology and Population Health at Stanford University. He's also associate professor by courtesy at the Department of Statistics and the Stanford Prevention Research Center. His work is around behavioral interventions and their evaluation, and he's interested in developing causal inference methods that are transparent. A good example of these are two randomized studies of intervention to prevent sexual assault in settlements in Nairobi, Kenya. Professor Baiocchi has extensively published in prestigious journals such as Annals of Applied Statistics and the American Journal of Epidemiology, and also Biometrics. I would like to give you the floor. Please be aware that we are lucky to have today two speakers, including Jordan Rodu, who is with us also today. The floor is yours. They will take questions at the end of the seminar.
Thank you very much. And thank you for inviting us to talk today. When I first accepted this session, I didn't realize I was going to have the opportunity to be here in Virginia with my colleague, Jordan. Jordan and I started together as PhD students in the Department of Statistics at the University of Pennsylvania. So this kind of research, this talk that we're giving you has been building for like 10 years. So again, we trained as classic statisticians, sort of slightly different parts. I was really into causal inference when I started, and Jordan was more on the machine learning side of things. And so while we diverged for a while, we really came back through this research together. So starting here, what I want you to do is to think about what's the difference between classic statistics, and machine learning. If you're really trying to understand what makes them different. And I think, just get this out of the way, this is probably the most important thing, machine learning is cool. And old stats techniques, maybe not so. And we're trying to like answer today, like, well, what does that really mean? You know, what really is machine learning, and why does it, especially to people raised up in statistics or traditional statistics, what makes it different? And I think it's, you know, it's an important question that we need to answer. Why is machine learning different, or why does it feel different? Because we keep ending, because we don't have that tight definition, we end up in these weird, confusing debates. Like, so people will be like, hey, is lasso a statistics method, or is it a machine learning method? And you know, I can sort of see a couple different ways. Like, it's got some new innovative processes to it, but maybe it was built largely by some statisticians. Like, how do we go about adjudicating it? And I think if you ever want to get a statistician kind of like fiery, you tell them that logistics regression is a machine learning tool. And so I'll pause here and sort of ruin the surprise. I think there's actually a case to be made that logistic regression can be used in a very clearly machine learning way that is not the way that a statistician, when he or she thinks about logistic regression from classic statistical theory, is thinking about it. And so what it's going to come down to is we're going to try to convince you that there's different ways of thinking about algorithms. And it's really important to be able to tell these apart for a number of different reasons. So that's what this talk is really about. So this whole project kicked off because traditional statisticians, folks who got raised up in the old sort of like, paradigms, can feel that machine learning is different, but articulating, particularly to our colleagues who are applied researchers who understand that machine learning and AI are making big progress, and they want to bring it on their own research, they ask us to do this, and we're like, something doesn't feel right, or something doesn't feel comfortable to me. So the big takeaway from this talk today is the difference between machine learning and traditional statistics is not about the algorithms. I want to anchor on, like, because that's where a lot of the conversations are. Hey, is lasso new or old? Is logistic new or old? It's not about the algorithms. It's about how we use data to reason about the performance of the algorithms. Okay, so this is the big takeaway. And then that sentence may not make sense at the beginning. We'll return to it at the end, and you'll probably feel very comfortable with it. This is all work that we just published this spring in the Journal of Observational Studies. We're going to be giving talks on this all this fall into the spring at different statistics departments. So today, to make this concrete, we're going to start off with 3 projects: a randomized trial, a model, and a machine learning project, convolutional neural net kind of thing. And we're going to use these 3 studies not because they're like, because they're largely using 3 different styles of data science, 3 different styles of reasoning using data. So for the second half of the talk, we'll be doing the theory, or the sort of more abstract department. We're going to be talking and naming the characteristics of these 3 different styles of reasoning. So warranted reasoning, model reasoning, and then the new one that doesn't get talked about a lot, and that's what we're trying to change, is outcome reasoning. So warranted reasoning is kind of like randomized trials and sampling. Model is more like, linear models, and outcome reasoning is the new one, and we'll tell you about that. So when I use the word reason, we use the word reasoning. What we're thinking about is there are different styles of looking at empirical facts that we generate, so summary statistics, in order to determine how much we should trust the conclusions being drawn. So if you grew up in old classic stats, you know warranted reasoning, you know model reasoning, and especially if you're in the causal inference literature, that's sort of like maybe like design thinking versus model or structural equation models. And we've been taught to really differentiate and know those two, but that third one keeps coming up and we just don't recognize it. That's what we're going to try to do a good job with today. So let's talk about that first project. So during the introduction, Dolores did a wonderful job of introducing. So we do a bunch of work on sexual assault prevention in Nairobi, Kenya. And so I've been running randomized trials there going back almost 10 years now. So this is a picture from I believe it's Kibera. And so you can see like this is a tough environment. You know, those walls are made of mud and tin, and you know that's an open sewage pit there, chickens running around. In some of these areas, like the rates of sexual assault, rape are about 1 in 4 women in high school will be raped in the prior year. So that's why we've been deploying this set of interventions there for a while. And me and my collaborator, we go in country and we talk with school administrators and talk with students in order to get our program into these settlements. This talk is not about this intervention, but if you ever want to hear more about it, we contact us and we tell you more about it. But there are these phenomenal trainers who go in and they teach a curriculum. It's called Empowerment Self-Defense. There's been a series of randomized trials across the world. There's another phenomenal team who's doing this kind of research in Canada with college-age women. And all of us have sort of concluded that this is a very effective program. It mixes both social cues and dynamics, and then also teaches them physical self-defense. I've got a little article down here if you want to read more about it. But it's a pretty amazing program. And our first randomized trial that we ran on this, we were able to demonstrate a 50% reduction in rape. So this was, and I'll pause here to say, so on the empirical side, how did we demonstrate that claim? Well, we did a cluster randomized trial. We went, in this study, we went out to about 30 schools and metaphorically flipped a coin. We introduced a stochastic process, a random process in the world, and then we went through and measured things. And then the inference followed from that. All right, so we went into the world, generated the kind of data that we needed in order to reach that conclusion. I know that's like sort of basic stuff, but I'm going to come back to that in contrast with these other 2 forms of reasoning on these other 2 projects. So, second project. This one's really using model reasoning, and this is still working on this sexual assault prevention project in Kenya. So after our first randomized trial, we came back and we ran a second randomized trial, and much larger in Kenya, very similar to that first one. But now we had 2 years worth of data. So we had a baseline period, second, third. After our first period, when we were looking at that baseline data before we had collected the end-line data, we noticed that some of the responses that we were getting were inconsistent. So if we asked 10 questions about being sexually assaulted, maybe a young girl, like a middle school girl that we were working with, she might say, I've never been sexually assaulted. And then a couple questions later, she might say, I was sexually assaulted by a neighbor, something like that. And this is not terribly surprising. If you've done work in this area or any time pretty much with humans, you end up with like inconsistent results. And in this case, this is a complicated idea. It has to do with like maybe these folks are young who we were working with, maybe sort of the confusion of what's going on with consent or something like that. And also maybe there's some tough stuff about like the challenges about like, if I report that, the next door neighbor assaulted me, maybe there's, I'm going to bear consequences, or maybe they're going to take him away, and maybe there's some like emotional bonds there. It's a very complicated dynamic. But we have theories and we have background on why we think someone in this situation may not be giving us totally consistent results, okay? So what we did when we saw these inconsistent results, we wanted to adjudicate it. We wanted to think about like, what's a principled way of using our data to say, if we get an ambiguous answer, should we think of it as more of a no, or should we think of it more of as a yes? So we did something relatively simple. We built a logistic model, and we said for people who the unambiguous yeses, unambiguous nos, let's regress that on a set of covariates, x1, x2, x3, and see if we can sort of get some sense of how the covariates map or the question responses map, such that maybe the ambiguous people, we can then get a good sense of if they're more like the yeses, more like the nos. So let me pause here and say, that's different, very different than what I talked about just a minute ago with the randomized trial. I am positing a model. I'm sort of saying, I think it might be roughly approximated by a logistic. Maybe, and then I'm also doing some things where I'm sort of referencing some of the theories of like why we think the girls might respond in a complicated, internally consistent way. But I haven't generated that data. I didn't go into the world and say, you must answer using these, like look at your covariates and generate that. So already, I hope it's pretty obvious, but and again, if you're a classic trained classically statistically, you know that there's this difference. But we'll return to this again. But both of these are very reasonable ways of advancing. So the third project is a human trafficking project. So this is a very new set of studies that our team at Stanford, the Human Trafficking Data Lab, have been running. we've been operating in Maranhão, Brazil, with federal prosecutors. Maranhão is right on the arc of deforestation in Brazil, and it's a tough, in this area it's tough because the economic activity there is maybe not what the folks locally would want. That area can be clear cut and so like in these sort of like heavily forested areas, it can be clear cut for kind of like two reasons. One is once you clear cut it, you can now like put soy crops or maybe like raise like beef cattle there, but also you can get now access to some of the minerals and that kind of stuff. So deforestation is happening a lot, and it's happening sort of away from population centers. And when they do that, they typically take younger men or men of not strong social connections, typically from like some of the favelas, some of the settlements there, and they promise them jobs out in these remote locations, and then they stop paying them. They stop treating them, like normal workers, and it's very quickly that a lot of these situations deteriorate. So this picture here is one of the sites, one of the locations, and these little domes are ovens. So when they cut the trees down, they process them in these ovens, they cook them down to charcoal. That's what these little black pits are, or the piles are. And when the federal prosecutors, when the Brazilians are trying to deal with these, what they have to do is they have to typically rely on tips from folks. And the tips will come in and they'll be like, hey, I can sort of smell smoke, it's a couple miles up the road or something like that. But these are really remote locations. So these folks who have been running essentially these slave labor camps, these deforest operations, don't get found very quickly. And that has to do with a lot of the logistics. But I'll tell you, we've had a lot of success because we're using satellites and it's so easy for us to find them. This has been a very exciting project for us. This is some data from Google Maps, but you can see this same site from the air has some really nice distinct patterns. Those charcoal, the coloration there doesn't look like the rest of the rainforest, right? It's very dark. And also right now, these bad guys are lining up the charcoal in straight lines, and our machines are just picking that up. Nature doesn't do a lot of straight lines. So we're using some very basic convolutional neural nets, mostly stuff pulled off, like just straight out of the box. And we're using cheap satellite data in order to find these locations. So it's really, it's a nice win for machine learning. And part of the win is something like this, just to give you a sense of like how we're partnering with the federal prosecutors, with the folks inside of Brazil, is so historically we can look at their data and we can see that, hey, like they ran an operation at this one site back in 2019, and when they went in, they moved a bunch of people, like inspectors there, about a dozen people in. That's hard to get to. And when they went there and they evaluated, they found 5 people who were being trafficked, who were essentially in slave labor. When we look at it with our data, we can see that there are actually 2 other sites very close by that they were not aware of at that time. And if they had deployed, we think they probably would have found a few other people. So we've set up this convolutional neural net. We can run it really cheaply on cheap data. And we can find a bunch of sites very easily that typically the federal prosecutors weren't aware of. And also, I'm particularly proud, we can now build GIFs like very quickly. And so we can basically, you can see that these sites are active or not. So, our stuff will find a location and then build out this little, sort of like time series thing. So the federal prosecutors can determine, is this an active site, should we deploy? And then just recently, just in July, we went on our first pilot test. We worked with the federal prosecutors. This fellow here delivering this is Luis Assis. He's a federal prosecutor in Brazil, and he's talking about, he's prepping the teams the night before. There's a little article you can read about this. But we went in with security forces because these are tough situations, and we successfully found a bunch of people being trafficked. And we're very excited about this. Clear win using machine learning. There's I feel bad telling this about this story so fast because we're going to focus on the data part of this, but I think this is a good win for thinking about how machine learning in a high stakes environment can be used. So we can talk about that later if you want more. So 3 different projects, and the reason we're doing this is because like we want to ground this conversation in like there are different styles that are appropriate in different situations. They sort of return different guarantees. That third one, if you've never done sort of like modern machine learning, if you try to look around, we didn't run a randomized trial. We didn't do any sampling in order to do the human trafficking stuff. I didn't write down a model and think about the error terms and that kind of stuff. It's somehow emerging from a different style of using data. And I think if you think of, in terms of like, one way to see how these are different is maybe say, okay, when one of these studies is being challenged, or maybe there's a failure, how do we fix it? And so let's go into that now, and that'll help, I think, make it clearer how these are distinct. So like I mentioned, we've run a series of randomized trials on the sexual assault prevention intervention in Kenya. In a replication trial, so the second time we ran it, we got one of the most null results I've ever seen. We just looked across the board and we didn't see any difference between the intervention and the standard of care. And that, you know, we were thinking would be like more like a 50% reduction. And so there's a lot that goes on in that story. But one of the things that we did was we handed over all of our data and our analyses to other research teams, and we said, hey, kick the tires on this, look through and figure out what might have gone wrong. And during that process, I'll tell you, almost everything hinged on this kind of stuff. How did we sample girls to be in our study? Did we implement the randomization the right way? Did we look at, like, if we look at the treatment and control groups, did they look the same in like one of those balance tables? So it was a lot of like, did the randomization, did the measurement of the girls, did the sampling of the girls, did all of that actually in the real world comport with, did it match to what we had proposed on our protocols? And that's important to say because like what we're basically looking for is the fidelity of our stochastic process of our randomization that we put into the real world with what actually happened, right? Like, so we proposed something, but did it actually occur in the world? That was the question. No one ever questioned about our analytics afterwards, because that's not the weakest part. In a randomized trial, it's the fidelity to the intervention implementation of the randomized trial that is really the sort of weak point of a warranted or design-based inference. How about that model? How about when we were thinking about that logistic model to help us disambiguate some of our answers? Well, I'll tell you, when we were getting ready to do this, remember what we had were data from our baseline, and then we were going to lock in a way of adjudicating before we got, you know, these internally inconsistent, before we got to the end line. And so what we were going to do is we're going to commit, right? We were going to say, here's a protocol before we see the end line data for resolving these ambiguities. And so we internally as a team really double, triple checked things. And what we mostly did, you know, were sort of the classic stats things, which is like, check the reasonableness of the assumptions. Did things look linear in the ways we wanted them to? Thinking about like things like, you know, pseudo residuals in their behaviors, like that kind of stuff. But then we also, and this is the more classic one that we teach in our entry-level stats classes, is we looked at the fits on those betas. Did they match what we knew from the literature? If we thought a beta should be positive, was it positive? If not, like, can we think about, you know, modeling-wise, why that might not be the case? But these are the two ways that we sort of reasoned about this model, you know, before committing to it. And then another way to think about like modeling and how it's different from warranted reasoning, from design-based reasoning, is that you know, let's say we got to that end line period and our adjudication model wasn't behaving well. It's very reasonable for someone to say, hey, your model didn't have that squared term. And I think, based on my own intuitions about the world, that this is the real, or the better fitting model. And in some ways, like, I just want to point out, and this is known, I'm not sort of saying anything new here, is like that's the way that people fight with models, is because they're all contingent, because we're all proposing, they're all hypothetical, someone can push back and say, I don't believe that. And it's much harder to do that kind of like, I doubt you from the base when you're doing warranted, because it's like, well, I went into the world and I randomized. And you can criticize about like maybe exactly how I implemented it, but we agree that that is like something that was like done in the world. So that's a big part of the departure between these two styles of reasoning. And let's talk about this third one. So this is the human trafficking. So when we were warming up for that, going into the real world part of it, what we did is we sort of we handed over 11 locations to the federal prosecutors and said, how about you, when sitting at your benches, sitting at your desks, just sort of evaluate these as if they were kind of like tips and see what you would do. And so they went through their desk evaluations of these 11 sites that our model proposed, our algorithm proposed, and they convinced themselves that 4 were active, 2 they weren't quite sure about, and 5 were false positives. And when you look at those 5 false positives, like that's a big miss rate, right? It turns out that our algorithm is like basically a toddler. It's like a little kid, and like much like a toddler, it learns really, really fast, but it also loves water. It's like obsessed with rivers. It's obsessed with like lakes, and it loves, like, it will go out of its way to talk to us about water. And we can't figure out why it does that. Even when we patiently explain that we would like to look at these like sites, it still goes to water. So that's kind of a failure, right? Like of the 11, 5 of them were not, what we wanted. So that's a pretty high fail rate. And so I don't know how to fix that, because in some ways, like this is a black box. Like the way that the convolutional neural net is mapping the variation in the covariate space to its outcome, I can't interrogate it the way I could with that logistic regression. And I'm not saying that will always be the way. There's going to be someone very smart who figures out that there's some substructure, latent structure that's mathematical, and we can talk about parameterizing it. That's going to happen at some point. Someone's going to do that. But at the moment, what we're doing is we're adding more observations. We tell it, okay, no, you got this wrong, or here's some new sites that we hand coded. This really is like one of those sites, and we help it learn from that. We retinker with its weights, and we sort of assign different attention features to different portions of the field. And then the important thing for us is we've also added a human into the loop. So now what we do is whenever the algorithm thinks it's found a location, we requisition high resolution satellite of that area, and then we put that very high resolution information in front of a human. So again, like I didn't interrogate parameters, we didn't look at residuals, but there's something else going on with this third type of data science. I still am going to claim that like there's something good happening here. I'm not trying to say the other ones are better, but it's distinct, right? This third one is somehow operating in a different way. Okay, so now we're going to get into more of the sort of like, let's just tell you more directly about these 3 different styles of reasoning. I'm going to start with the old ones that are sort of more traditional in statistics, then I'm going to switch, and we'll switch over to Jordan to talk about the new one. So warranted reasoning. Warranted reasoning, the classic example is randomized controlled trials, RCTs, but also like sampling, like a survey or something like that. We use the term warranted because Fisher was the first one to do that. So Fisher referred to randomization using RCTs as the warrant for inference. And what he was basically saying is that when you randomize, it gives you permission to run all of the randomization inference after that. So permutational t-test, Fisher's test, n-test, u-test, like that kind of stuff is now permitted by the use of a randomization. It's our strongest form of inference. That's why like the Food and Drug Administration in the United States always requires a randomized trial. I'm sure like all of the evaluations that happen there for these high stakes sort of situations, we want our inference to be true by construction. So someone reached into the world, they did something, and that's what then made the forms of statistical inference true after that. And it's that connection, that tight connection to the real world that's why why Fisher called it warranted. And I just want to make a quick connection is you see this in other parts of mathematics, right? Like geometry has the reputation for doing this as well, like, going back many, many generations. And because geometry can be brought into the world, and it can be brought back out. Like you can think about using, like if you think about like all the properties of a circle, well, if you have a compass, you can approximate that, circle. And when we think about like, is everything we know mathematically about a circle, does that hold true for this thing I just drew? Well, you start interrogating, well, how well did I approximate? How rigorously connected to that theoretical was this process that gave rise to it, right? That sort of debate, and that shows up in engineering a lot. And nowadays, you can see it with like computers. Like computers do this with like set theory and number theory and that kind. It moves these discrete math, moves it in and out of the world. So we see that with warranted reasoning. You don't see that as much with models. To emphasize this, when we assess the rigor of a warranted reasoning kind of problem inside of statistics, we think about how well did the randomized trial, how felicitous, how well did it comport with what we thought we would be doing, right? Then after that, the inferential steps are less debated. Okay, so, and by the way, like the Nobel Prize was just awarded for this a couple of years ago. The economists, pictured here, what they did was basically notice that they could say, in the real world, there are things that almost behave like warrants, that almost behave like randomizations, these natural experiments. And if we predicate on that, we can do something like a pseudo warrant. And what they did was they basically shifted a lot of econ away from using model reasoning, over to something that was an approximated warranted reasoning. You can debate whether that's good or bad. I think personally it's great, and I think it's amazing, and the Nobel folks did. But another way to say what they were doing was changing the style of using data. They were moving it toward an approximated warranted reasoning. Let's talk about model reasoning. In particular, I'm just going to talk about linear models as my working example. But so first thing to notice is that models are propositional. We hypothesize that there exists a known function that gives rise to the data we're about to analyze. And if we suppose, or if we assume that that model is correct, then it's really amazing because we can now interrogate the different pieces of the data generating function. Usually we use these to really decompose the different parts of the covariate space and attribute that variation to how we're going to be using it in the outcome space. So it's a lot more detailed, that mapping. And let's just take good old linear regression. So here we've got a bunch of things about sort of additivity and the linearity of how the x's relate to y. And that's really fascinating, but it's also not we're not saying that we have made that true. If you're very careful about what we're saying we think the data in front of us are well approximated, right? We also have some mathematical properties and stories that we tell about the behavior of the error terms and that kind of stuff. So it's all, again, propositional, theoretical, and maybe it's doing a good job, right? Over and over again, oh my goodness, linear models just keep doing great things. They're very good at giving us good predictions, and even the beta coefficients are really good places to get your intuitions running about maybe the actual causal properties. Not that I'm guaranteeing causality, but it gives you sort of good intuitions. It usually behaves very, very well, even though it's not tightly bound to the real world. It's very effective. But if you think about how we debate models, it's usually, again, like I talked about earlier, there are two ways to do it. You attack the assumptions, or you look at the parameters and attack those. So in the assumptions, we are interrogating a linear model, we look at the compatibility or the incompatibility with linearity, additivity, independence of assumptions. And if we see, hey, the residuals don't look very independent, I'm going to start doubting any inference that's predicated on this model. Maybe I'll even switch to a different model. But if I interrogate those assumptions and I see that the data aren't comporting with them, they're not compatible, I'm not going to follow your inference. I'm not going to believe your inference. And then you can do that same kind of thing with parameters, but it has a slightly different role. The reason we teach our students a lot about parameters is basically those beta coefficients oftentimes. So let me give you a quick example. Let's say we're predicting the amount of calories someone will eat, and x1 in our linear model is someone's height. If I tell you that beta 1 is negative, if I tell you that someone gets taller, if there are taller people, that they tend to eat less or fewer calories than people who are shorter, that's surprising. I mean, most of our intuitions, based on everything we know from previous studies, from our own intuitions, that beta coefficient should be positive. So when you do that, part of the reason that models are strong is because we can link back to other sources of data, other studies, and map those. So that's another reason models tend to be very strong in how we're using data and thinking about the compatibility. I'll just mention briefly, one of the different fields about model reasoning is that when you look at your data, you have all these different models that are built and ready to go for different kinds of situations. And we spend a lot of time teaching our students to recognize those. The last sort of set of thoughts about model reasoning before we hand it over to Jordan, talk about the new outcome reasoning way. Everything I just said about models was summed up really well by George Box a long time ago. All models are wrong, some are useful. And I think this is just we all love this quote as statisticians because it rings true. What he's saying, I think, is that all models are propositional. we didn't force them to be true in the way that we can with a warranted reasoning, but over and over again, they tend to be useful. And I want you to walk away with that. Everything I just said is more detailed, but Box got that so right so quickly. But I want to make sure that we all notice that models are really vital in our tools for reasoning because they allow us to think very carefully and decompose variation in a way that warranted inference often can't. Maybe you could run a very complicated multifactorial randomized trial, and that might get you something closer to a model. But model reasoning is a very elegant way of getting a lot of detailed information. And it also allows us to think about questions that just really aren't well suited for warranted reasoning. I'd like to hand this over to Jordan to really give you the new sense.
Okay, thanks. So I'm going to talk about outcome reasoning now, this third form of reasoning that Mike was earlier talking about. So a little bit of background about the common task framework first. Much of the rapid success that we see in machine learning came from this infrastructure provided by the common task framework. If you haven't heard of the common task framework, David Donahoe released an article a few years ago called 50 Years of Data Science. It was one of the first introductions to at least the statistics and data science communities of this common task framework. And it's still relatively unknown, but we find that people are starting to become more and more aware of it. So a good example is the Netflix Prize. It's a common task framework that was run in 2009. It was a relaxation of the original common task framework, but shared a lot of the properties of the original. Also, Kaggle competitions, things like that, often tend to look a lot like a common task framework. Again, they all tend to be relaxations. So the common task framework starts with a curated data set. It's available to everybody, so everybody's working with the same data set and it's fixed. Unlike in statistics where you might generate your data through a warranted reasoning, or you might have to collect your own data, this is a fixed data set. The task is described. What do we want to do? We want to give you a set of covariates and we want you to predict y. And then they're going to tell you how they're going to measure your performance. So for instance, a mean squared error between the actual observation and your own prediction. Then there's a held out data set that's reserved for evaluating the performance. And in the strict common task framework, no one ever gets to see that held out data set except once at the very end of the competition. This is where, for instance, Netflix, a lot of Kaggle competitions do diverge from this strict common task framework. And then at the end of the competition, we just line up the set of algorithms. Who did best in terms of that metric that was given for performance? And it gives us a really easy way to compare across different algorithms. We don't have to go carefully think about all the mathematics or what do these coefficients mean. We just see who did better, and that's sort of the winner of the competition. It's incredibly fast. Again, machine learning has been innovating incredibly quickly. It's low friction in the common task framework. We don't have to worry about our link to sampling. There's no link to a data generating function. We don't care what the original data generating function is. The ground truth is directly observable. We have the actual observation to compare our prediction to. Relative performance is assessed by a target metric. So again, we don't have to worry about interpreting the algorithms. We just look at the final metric to see which one did better. And finally, a computer does a lot of the work, which is great. We don't have to worry about building the mathematical machinery for these algorithms. The computer, we have great algorithms, obviously, to fit highly complex algorithms. So this has allowed us to innovate much faster and with many fewer restrictions than in the traditional statistics or model reasoning community. By the way, I do want to, well, I'll get to this in a minute. So if you want to learn more about, the rise of computation, you could look at Tukey Sunset Salvo, where he basically lays out, he says mathematics is really hard. Computation is, much lower friction. We should think about pivoting to, at least introducing a lot more computation in our statistical work. And Breiman, Two Cultures, he really started to describe the algorithmic culture and compare and contrast it to the model culture. But the common task framework has really led to, from our standards, wildly complex algorithms that don't rely on any mathematical description. So you can think of, large language models, for instance. If someone doesn't describe those as wildly complex, I don't I don't know how to relate to them. So the basically we don't have to worry about the mathematical description of how an algorithm takes variation from the covariates and then makes a prediction from that variation. So this has led to a lot of these black box algorithms. But the CTF is also kind of broken. So I mentioned that there's a relaxation when we look at the Netflix prize, but there are a lot of other relaxations. So if you're a data scientist, you've probably run your own CTF on your computer, even if you don't realize it. And there you don't have a held out data set that you really cannot look at. And so as best we can tell historically, this common task framework that was developed for human language technologies in the 80s, 86, and it was run by a US agency called DARPA. They were the ones that administered the first CTF. And the idea from DARPA's point of view was we have all of these different subfields of human language technologies, and they're all sort of running into the same engineering challenges that we need to overcome. And so if we can provide a competition whereby people work on this little tiny challenge in a very clear way, we might be able to make a rapid progress in all of the subdomains. And every year is very carefully administered. So they very deliberately chose a data set. They chose a prediction problem. They very deliberately thought about the metric they were going to use, et cetera. And it was not developed to deploy these algorithms in the wild. So these were just to overcome these engineering challenges, and any kind of deployment was still decades away. So they weren't really worried about thinking about how these algorithms should interact on real data in real time. That was a long time away. So nowadays, like I said, we're at the age of deployment. Algorithms are developed one day and deployed the next. And we don't have this careful framework. Not only has the careful framework sort of become just a part of the culture, and so we're not really thinking all the time about how we're going to move this framework forward, but we never really developed a framework for deploying in the wild. And so that's led to some problems, some high-profile stories where an algorithm has sort of tragically failed, and at the end of the day, we don't know how to talk about it. We don't know how to reassure people that this was the right move, or that failure, it won't fail again. And so the question is, how are we supposed to make sense of deploying these algorithms? And there are a lot of folks that have started to work on this. This was first brought to a lot of people's attention by Ali Rahimi at a conference where he said machine learning is alchemy. That led to an interesting debate following that statement. But he was proposing we really try and, almost halt. I mean, I don't think he really intended it, but almost halt the progress of machine learning until we could figure it out. A lot of folks in Fair AI are working on ways to fix how we train these algorithms to remove a lot of biases. Cynthia Rudin, for instance, thinks a lot about machine learning in high-stakes scenarios. But there's another way to think about this. Instead of trying to fix the way that algorithms are trained, we could take a broader view and say, well, let's just keep training algorithms the way we do. I mean, we could try and fix them, but for the ones that are being trained the way we train them inside this sort of pseudo common task framework, how can we deploy them in the wild? How can we decide if they're appropriate to deploy in the wild? And so Mike and I decided not to confine ourselves to how do we fix sort of training and machine learning, but more think broadly about when are they appropriate to use. There's a group at Princeton that's doing something similar. Arvind Narayanan and his lab have been doing a taxonomy of machine learning. They have a whole collection of machine learning algorithms that have been deployed in the wild, and they try and look inductively for rules as to why some succeed and why some fail. They have a great website if you want to check it out, Against Predictive Optimization, where they sort of go through these different ML tasks and their features, and sort of which ones have shortcomings in which areas. Mike and I worked out this more general framework that we call outcome reasoning. And what we're doing is we're proposing essentially that we think about outcome reasoning, develop this framework of outcome reasoning for the deployment environment, rather than only focusing on development. And again, there's a link to our paper if you're interested in. But basically, outcome reasoning focuses on evaluating performance purely in the space of the outcome, just as a reminder, by passing a detailed evaluation of the mapping of the covariates to the outcome. So we don't have to worry about that evaluation. But we thought, okay, given that's what's happening, what are the really important features of the CTF? Because we're no longer linking sort of the behavior of the algorithm and our understanding of the behavior to the predictions that it's making. So why do we trust the process so much with machine learning? What are the important features that allow us to trust a machine learning algorithm? And we looked at the CTF to figure out what are those features of the CTF, that if you have an algorithm that's successful in the CTF, that you say, yeah, I think this is a nice algorithm. And we abstracted these features to understand what would be required for us to know for a prediction problem in the wild, so that we'd be comfortable using that machine learning algorithm in the wild. Okay, so we're really focused on what are the features of the prediction problem that we're interested in, not the features of the algorithm. What are the features of the prediction problem we're interested in, to giving us security and certainty that we can indeed move forward with outcome reasoning. And I'm going to contrast this, by the way, to model reasoning. We're going to deliver on that promise to help you with collaborating with applied folks. This is what I'm going to do now, so that you feel comfortable talking with your applied folks about is machine learning appropriate for this context. We're going to introduce 4 key features of a problem that you can call out and discuss with your colleagues to help decide if you want to use outcome reasoning or model reasoning, which one makes sense. We're going to contrast outcome reasoning and model reasoning, because they're the two that get confused a lot. Like I said, whenever you talk to collaborators, again, like Mike said before, is the lasso outcome reasoning or model reasoning? Is it? These are the two that tend to get confused a lot. Some, just as a side note, some have proposed ways of using warranted reasoning to investigate black box algorithms, which is really nice. So Tyler McCormack has a paper that we encourage you to check out. It's really super interesting way to try and sort of bring these 3 forms of reasoning together. Okay, so when we describe a prediction problem, there are 4 features that must be satisfied in order for a black box algorithm to be deployed. And again, we've taken these from a careful study of the Common Task Framework, where these algorithms are developed. So the 4 features are measurement. So can we actually observe some sort of measurement of the function, the outcomes, and of our predictions? The second is adaptability. Can we adapt? Can we update our algorithms on a useful timescale? The third is resilience. Do we have a high tolerance for accumulated errors? And the fourth is agnosis. Do we have a high tolerance for disagreement with our domain beliefs, our scientific knowledge, ethical concerns, etc. And for a lot of folks working in fair AI, that they sort of fit into that 4th category there, that 4th feature. So we refer to these collectively as MARA, hopefully for obvious reasons. So it turns out, though, that if you were to go through and ask these 4 features about your problem, it can change depending on who are stakeholders. And so we've really augmented MARA to have an S. It's a function of the stakeholders. So different sets of stakeholders might have different concerns. And I'm talking both about primary stakeholders, the ones who are actually deploying the algorithm, and secondary stakeholders, the ones that could be affected by the algorithm. So depending on who we include in those categories, a machine learning algorithm or outcome reasoning may or may not be appropriate to use, and that can change depending on who's there. Yeah, go ahead.
I just want to point out, like, we're maybe emphasizing stakeholders here, but that's like stuff that we've done in randomized trials forever, and we've done it even with like models when those get deployed in the real world. And we're just noting some of the anxiety about machine learning and deploying AI is the fact that people were missing the fact that there's some really easy questions for identifying which problems are appropriate for ML reasoning, for outcome reasoning, and which ones aren't. And that's where you involve stakeholders. And we're just recentering like stakeholders here. Maybe it sounds like overly flowery or something like that, but we do that in randomized trials, we do that in modeling. We're not doing a good job right now with that inside of machine or outcome reasoning, machine learning kind of stuff.
Yeah. Okay, so outcome reasoning deployment. So there are 2 types of reasoning, obviously, for in a framework. So there's outcome reasoning. If the stakeholders agree that the problem satisfies all 4 more problem features, then we can deploy the algorithm. And importantly, we debate if it's working after watching its behavior in the real world. And this is what a lot of times when people have deployed an algorithm and we're surprised that it fails, The key is that they decided that the algorithm was definitely going to work prior to deployment. In reality, with outcome reasoning, you need to be watching it after it's deployed, and that's where you decide ultimately if it was a success or not. And so just to, kind of a visual here, we have the 4 decisions that someone has to make. If you say yes to all 4 decisions, you can be in a black box. So the outcome reasoning is actually perfect for black box. Both Mike and I would say if you can use outcome reasoning, you probably should use outcome reasoning. It's a great tool in these situations. However, if any of the problem features fail to satisfy, then you really need a model that can be reasoned about independently of the data used to fit the algorithm. So you have to be able to look at the actual model independent of the data. I'm not worried, was my training data set representative enough, etc. I'm going to look at the model itself and make decisions about the parameters and if they're suitable for deploying in the real world. It requires a mathematical foundation that allows for this deductive reasoning about the future of algorithms. Again, just to go back to the example of a linear regression, if someone looks and says that beta less than 0, that's kind of weird. That's something that calls question to whether or not this model is suitable for deployment. There we go. Okay. So again, to reiterate, outcome reasoning happens after deployment of the algorithm in the real world. Just like in the CTF, you don't decide that an algorithm is good before you've run it. You look and see how it does. Once it's made its prediction, you say, oh yeah, this algorithm actually improved my prediction error quite a bit. Same thing when you deploy. You can't really reason about how an algorithm is going to do prior to deployment. You have to deploy and then say, look, we're getting really good results. So everyone has to be, all these stakeholders, these primary stakeholders have to be comfortable bearing the consequence of its errors as error accumulates. On the other hand, model reasoning allows you to go through and discuss prior to deployment whether or not an algorithm is suitable to deploy before any errors begin to accumulate. It's vital that we get stakeholder buy-in on the type of reasoning that we use, because errors are certainly going to occur, and we're going to get pushback from when errors do occur, and we have to have a story that we have to take accountability in a way that we're comfortable with. And so, if you think about the 2 ways of accountability from outcome reasoning, often it's, yeah, we're trying to make it better, we're giving it more data, we don't really know why it's working, we try to avoid that situation, etc. But in model reasoning, you could say we had all the experts come together and they all agreed, yeah, this might make errors, but this is the best way that we can move forward. So it's 2 different levels of accountability there. So just to give a visual timeline here, there's deployment. Again, model reasoning, you get buy-in for deploying the model prior to deployment. With outcome reasoning, the only way you can validate if it's working is by looking after the fact if it's actually working on real data. This is all both independent of actually building the pipeline. So we're not really taking into consideration what is the data that went into this, et cetera. We're thinking just about, again, either examining the model from a mathematical perspective or looking at the outcomes. But what's important about where this pipeline sits is, when do we decide on which approach to take? And that's independent of the pipeline. We don't consider the the validity of using this algorithm versus that algorithm, or this model versus this model, prior to deciding on if we're going to use outcome reasoning or if we're going to use model reasoning.
I just want to emphasize that first bullet point there is a little bit subtle, but it's really important, which is that basically outcome reasoning is really good at saying, this is working right now. On this data set in front of me, things are happening that I like, or maybe it's not, right? We look at that metric. But unlike a model, it doesn't say, and here are the situations where I am providing guarantees for the future deployment. A model says, if there is this latent structure in these parameterizations, you will function properly in the future. You can get outcome reasoning to work better by doing some types of sampling on future sets, but that's not how outcome reasoning is required to work. So in our paper, we go through the detailed arguments for that first bullet point. So I just want to point out, if you don't follow exactly what's going on that first bullet point, it is a subtle argument, but we demonstrate it.
Okay, some final thoughts on outcome reasonings. The takeaway here is that the difference between machine learning and statistics is not about the algorithms themselves, it's about how we use data to reason about the performance of the algorithms. And so, we think about 3 different groups that are frequently involved with these algorithms: biostatistics, statisticians, and machine learning folks. And we really think that they all use all 3 types of reasoning types, but just in different proportions. And so it's really important for us to start thinking about outcome reasoning. This is the one that's not yet really been fully described yet, and we don't have a good way of thinking about outcome reasoning. And so it's really important, since it is a part of everybody's bag, that we really want folks to start thinking about it and thinking about its properties. The other thing that we're really focused on here is we need to start teaching our students and collaborators that there is this 3rd form of reasoning, and it does have properties. So instead of, like Mike was saying before, instead of confusing the reasoning that comes into play with machine learning with the reasoning that comes to play when we use models, we do need to talk about that separation, that there's this distinct separation, and that just like model reasoning is appropriate in some places that warranted reasoning isn't, and vice versa, it's the same story with outcome reasoning and model reasoning, and we need to make that explicit. Really, at the very end of the day, we need a language for actually defining and talking about outcome reasoning. And so that's one of the big things this paper is focused on, is creating that language and that framework.
And I think, in particular, when I think about the audience today, is in your skill sets, we're talking about also a mathematical language for outcome reasoning. I think Jordan and I and other people in the field have started to try to say, hey, there is this 3rd kind of reasoning, but people haven't done all the math, haven't done a very careful job of describing its mathematical properties. And when we do that, we're going to have a lot of advantages. Fisher and other folks people were running randomized trials for a long time before they started really talking about the mathematical nature of it. We were doing versions of least squares for a long time before, like, C.R. Rao really nailed down a lot of the key features. So I think there's probably someone out there in the next decade who's going to do a really good job of locking down the core mathematical structures that are required to make sure that outcome reasoning is very clean and carefully done. And so we just want to help nudge people along, and we've got a paper, and you can contact us if you want to talk more about this. So we want to say thank you very much for having us here today to talk with you all.
Thank you very much for your presentation, and for also giving us some ideas for new models that we may construct with the skill set that we have in this audience. I would like to ask the audience if there is any question that you would like to pose to Mike or Jordan. Quick question. I think I would like to thank you again very much for giving us a lot to think about black boxes, about fairness, about accountability, and about the differences between these methodologies in the type of work that you do. And to the audience, I would like to remind you that next week we are back, same time, and we will have a young session with 3 young academics, and they are the 3 of them female academics. So we are very much looking forward to next week talk. And to Anita, to Mike, and to Jordan, thank you very much again for coming today.
Thank you.